Okay, so we're back again. Sorry about that, but I've got an example of an uvular nasal as produced by Peter Ladefoged in spectrogram form. So this is what it sounds like. It's kind of like a really back engma with low F0. Anyways, this is the uvular nasal here in the middle. Here's his F1. So F1 and F2 for the ah, F1 and F2 for the ah, and then here we have it for the engma. So it's a little bit lower than 400 hertz, maybe like 350 or so, but it's in that neighborhood, right? It's going to be a lot lower than the F1 for the ah at any rate, and also lower than the F1 that you would normally expect for a schwa. So right around here. And then what you may also notice, or hopefully notice, is that with respect to the rest of this intervocalic nasal, the other formants are not very prominent at all. We get a weaker F1, which is lower in frequency than we'd expect for a vowel, and then our higher formants just kind of fade out. So what's up with that? There is a phenomenon going on here. So there's a couple things going on. There's overall damping, so we expect the sound of the nasals to be not as intense, just because energy gets lost in the passageways of the nose. There's also kind of permanent lip rounding in the form of nostril rounding when you produce a nasal stop of some sort. So your nostrils, not that you really want to pay that much attention to anybody else's nostrils, are rounded, right? And there's not a lot of sort of room there for the air to get through. So you get permanent, very tight lip rounding, as it were, that reduces the intensity for nasal stops the same way it reduces the intensity for a rounded vowel like oo. And then also the interesting fact that I kind of want to dwell on for a moment, though, is that you kind of lose resonance as well through what are called anti-formants. This is kind of a funny term, but it means exactly what it implies, is that rather than formants sort of intensifying particular frequencies in the signal, anti-formants will particularly suck energy out at specific frequencies when you produce a nasal sound. This, however, is only true of nasal stops with fronter places of articulation than the uvula, because you need to create basically an anti-resonating tube to get anti-formants. So there's no tube for air to get lost in when you produce an uvular, at least in the ideal case, because you're blocking off the passageway into the mouth when you create an uvular closure right here. But when you make a more forward closure for a nasal stop, you're going to create a side cavity in this whole passageway. So air would normally flow just through this open tube from the pharynx to the nose, but then some of that air, if it can, will flow here into the mouth. And you can look at this again, it's kind of backwards from the way we normally think about it, but now we've got a closed tube that's open here at the pharynx end. So that's going to resonate like an open tube of any sort, and its resonant frequencies are going to be based on the length of this side passageway into the mouth. Those resonant frequencies will be anti-resonances in this particular case, because the energy that would normally be reserved for this main passageway through the nose is going to get sucked into here, and kind of the sucking out of that energy is going to get intensified by the resonance of the mouth. So we're going to get anti-formants at specific frequencies due to this side chamber, and we will see those anti-formants as basically regions that fade out in the spectral characteristics of the nasal stop as you produce it. So that's fairly, you can see the overall pattern of an anti-formant in the nasal stop. It's kind of hard to figure out exactly where it's happening because it's energy that's not there, right? So it's just like a blank spot on the map, and it's hard to kind of pin down where it's centered. Ideally, you walk the math for that shows you how to determine what the anti-formant frequency should be are going to be based on the length of this vocal tract tube, in the same way that they're based on the length of an open tube of any sort. So let's just walk through an idealized example where we have a vocal tract length of about 8 centimeters. So if you remember, this length here was about 9.5 centimeters, and this would be about 8 centimeters to give you a total length of 17.5 centimeters through the pharynx and the mouth for a vowel like schwa. So let's just say that this length is going to be about 8 centimeters. What would the resonant frequencies of a tube of length 8 centimeters be? We use the same math as we did before, that same equation, but we just substitute 8 centimeters for our length. What do we get if we do that? We wind up with 35,000 centimeters per second divided by 4 times 8, or 32. If you crunch those numbers in a calculator or Excel, or in your head if you're feeling ambitious, you get a resonant frequency of 1094 hertz, which I'm going to label here as the anti-formant, or AF1 frequency for this tube. So that's about 1100 hertz, more or less. Like with formant frequencies of an open tube in general, you produce anti-formants going up the scale in the same way. So the second anti-formant frequency would be 3 times this lower formant frequency, so 3 times 1094, with some rounding off, winds up being 3281 hertz. And then the third anti-formant would be 5 times this guy, so something like around 5500 hertz. But we don't need to worry about that too much because that's already relatively high in the scale. And these anti-formants kind of wind up having other effects as well to make it hard to see anything higher in the frequency scale on a spectrogram than the first one. So here are some examples of that, or those two anti-formants in this speech sample we heard before.
Ma.
Of this word from Mandarin.
Ma.
I think it's tone number 1, but I can't remember if that means horse or something else, but it's that word. Anyways, where we see the anti-formants is right here. So right around 1100 hertz for F1 and right around 3300 hertz for, 1100 hertz for anti-formant 1 and 3300 hertz for anti-formant 2. And like I said, that's just where the energy gets sucked out of the system. They kind of coincidentally in this case will wind up being close to where we'd expect the second formant and the fourth formant to be for this articulation. So remember, our first formant for our nasal will be about 400 hertz, so the second would be at 1200, but the anti-formant is at 1100, so they basically kind of cancel each other out in this region of the frequency scale. Just doing the math quickly off the top of my head. So you'd expect another formant frequency that doesn't totally work because the third one should be something like 2000 or so on and so forth. But they're canceling each other out here at this part as well, maybe because you're shaping the vocal tract a little bit because you're producing an ah. But hopefully you can see that these regions of the frequency scale are not as intense as what we get for F1 and F3. So those are anti-formants in action. You don't really see where they are. You just kind of see what they take out, as it were, in the intensity of a speech sound. So when you have other places of articulation for your nasal stop, you're going to get similar effects, except that the anti-resonating tube in your mouth is going to be shorter. And because that tube is shorter, those anti-formant frequencies should be higher, right? So the overall length of that open tube is shorter. That leads to higher frequencies. For an N, reasonable length to expect would be an anti-resonating tube about 5.5 centimeters. So then we'd expect its first anti-formant frequency to be about 1600 hertz. We're going up the scale now. The second one would be 3 times that. For a palatal nasal, like nya, you get a length of about 3.3 centimeters. So that anti-formant frequency would be about 2600 or so. And then it just keeps on going up as you go back. So for engma, we have a tube of about an inch long, about 2.3 centimeters, and an anti-formant frequency for that would be 3700 hertz. And if you keep going further back, you wind up at the uvula, or an uvular nasal, and then the length just kind of goes away altogether, right? It's just too short. It doesn't really produce any sort of resonance or anti-resonance. Okay, my computer's starting to overheat here. It's not overeating, but that means I should probably keep moving. So this is an example of different anti-formants in this articulation. which is from a speaker of Tsonga, which is spoken in southern Africa. Saying that, which is nice because he has both an M and an N here. And you can see quite conveniently that we've got an anti-formant of about 1100 hertz here for the M. This is where the energy is being sucked out of the bilabial nasal. And then it's a little bit higher for the N. We'd expect it to be around 1600 hertz. So this is kind of where we're seeing a weakening in the intensity of this particular articulation. I picked this particular example because it works out nicely. It's not always that easy to see these anti-formants in nasal articulations in a spectrogram, but this is one case where it is. If you get really good and clever at this, you can start to see these sorts of subtle shifts in anti-formant frequencies when you're doing things like the mystery spectrogram exercises. But you really got to remember to pay attention because they don't kind of jump out that quickly at you. Other cues for nasal place of articulation would be, say, the transitions you get into and out of them, which look like the transitions you get for stop place of articulation, but we'll talk about that more next time. Yeah, and I got little arrows here, which I forgot about pointing out, where you should see the anti-formants for these two creatures. Okay, so in summary, what do we get when we see a nasal in a spectrogram? So we'd see periodic voicing because these are sonorant sounds. That means they're easy to voice just because of the way the tube is open at the end. So air can flow freely through your vocal folds without having to expect to stop at any point in time. The overall amplitude is going to be lower than what we get in vowels. We're going to see formants like we do in vowels as well because these tubes, the tube that you use to produce a nasal sound is going to resonate. The formants that we do get, though, are going to have broad bandwidths due to the damping features of the nasal passageways. There's going to be a low frequency first formant because the tube is longer overall through your nose than it is through your mouth. And there's less space between formants for the same reason because we're multiplying by odd numbers as we go up the scale, but the lowest formant frequency is lower, so the gap between them is going to be smaller for that reason as well. And then the higher formants are going to have a lower amplitude. So this is kind of one thing I forgot to mention, but I should. But one of the consequences of anti-formants is that they tend to not only suck out energy at sort of their center frequency, but they will reduce to a certain extent the energy above them in the frequency scale too. They kind of have long tails, as it were, in the frequency scale moving up. So that's why you normally don't really see much energy here. This is an unusual counterexample where you kind of get the F3 for the M here showing up nicely on the spectrogram. But as we see here, F1 jumps out as more prominent here. And the other formants of the nasal just kind of fade out. This isn't a great recording. Maybe that's another reason why, but we can hardly see like F3, F4 here much at all in the nasal. So don't expect to get a lot of information about this from these formants. You can just primarily with nasals, the main thing you get is like a clue that they are nasals as opposed to vowels, and everything else is a little tricky to identify acoustically. What's even more tricky than that, let's wrap up this lecture with this discussion, but what we get with nasalized vowel acoustics. So vowels can often be nasalized next to a nasal stop, and when that happens, you're getting a complex set of acoustic effects because when you produce a nasalized vowel, you're getting basically two passageways out of the mouth, one through the nose and one through the mouth, and they both resonate in their own way, and they both anti-resonate in their own way. And so when you wind up with a nasalized vowel, what happens acoustically is you get kind of a mess, to be honest, with lots of obscured formant transitions with broad bandwidths, which are hard to kind of pin down. So I'm not going to dwell on this in depth, but I will just say the acoustics of nasalized vowels are complex. So don't worry about them too much, but I'll just walk you through what I just said. You're going to get formants for the open tube through the mouth. You're going to get formants for the open tube through the nose. You will also get anti-formants for the nasal passageway, like the mouth will resonate in its own way, which sucks energy out of the formants that you normally get for the nose, and vice versa. So the nose is going to provide anti-formants for the formants you get through the mouth. And they'll all kind of be superimposed on top of each other and all also kind of cancel each other out. So it winds up often being hard to figure out where any formants are, just because they're weaker overall and they have broader bandwidths, which are make them spread out even more than what you normally expect for a regular vowel or an oral vowel. I guess I shouldn't be prejudiced about that. Anyways, but yeah, oral vowels are the unmarked case in language, and maybe this is one reason why these nasalized vowels are kind of special in that sense. Yeah, so I've got a nasalized vowel movie. I don't even remember where I picked this up. And it's not the greatest representation, but it kind of gives you a sense of what's going on. It's in French. But what you can see in this representation is what happens to the velum here. Opens and closes. It's going to open for the nasalized vowel. This is French, so it has
Le boulanger bu 11 bières.
A couple of nice nasalized vowels in there. Le boulanger bu 11 bières. I think it means the baker drank 11 beers.
Le boulanger bu 11 bières.
Please correct me if I'm wrong with that, but that's just one short of a dozen. Anyways, for the nasalized vowel, you open up your nasal passageway and air can flow out through your nose at the same time as it flows out through your mouth. So that's nifty. We can get some other examples here. This is from a language called Shinantec, and I present this in 341 as well, but what you might have noticed from that video is that you can open up that velopharyngeal port to a greater or lesser degree. Sometimes it can be more open than others, and this is actually a feature that is used in this language to sort of distinguish between partly nasalized and nasalized vowels, or I guess more nasalized vowels. And you can hear that fairly easily in these examples, I think. Yeah, so this one is just more nasalized than that. This is spoken down in southern Mexico near Oaxaca. And yeah, I think I already... Oh, so yeah, this you can see this as well on this classic X-ray film. Yep. Velum is open normally. When he's sort of at rest position, and normally, there we go. When he wants to make any sort of articulation, he raises the velum, so he closes off the passageway through the nose, like for de. But then there he is at rest position, where it's wide open, so he can easily breathe out through his nose. But when he makes that N, he raises it a little bit, right? He just doesn't close it all the way through. So there's not as much nasalization as he could have if he wanted to when he produces an N like that. Yeah, so you can sort of partly nasalize segments or completely nasalize them, or just that's a gradient feature of how this works when we speak through our noses. We can look at these in spectrogram form, and these again are not super great recordings. They have a lot of background noise in them. I apologize for that. But we can still see the formants relatively well here. This is just the oral vowel. So we got F1, F2 for the ah, and when we start to nasalize it, that F1 starts to fade away a little bit. F2 is still kind of jumping out here. You're also seeing like extra formants emerge here. And this gets more dramatic when we look at the fully nasalized vowel. But basically what you should expect are formants for your oral tract, formants for your nasal tract as well. Also, both of those formants will cancel each other out and smear the bandwidths, so it's harder to sort of figure out where the peak of that spectrum is. If you remember what it looked like when we checked out damped power spectra, that peak in the formant is just smoother overall and wider in terms of its bandwidth. So nasalized vowel formants are harder to pin down in frequency than oral vowel formants. And you can see this one is where it just kind of really becomes a mess, and it just looks sort of like a wall of intensity as we go up the frequency scale. And I'll mention just briefly, this is partly where that phenomenon of Jenkins comes from, rather than Jenkins. So there's a dialect region in the U.S. I believe this emerged in Tennessee, kind of in the Mid-South in the late 1800s, but where the contrast between two vowels like I and E was lost in prenasal stop context. The idea is that those vowels in that context were becoming nasalized because of the nasal that followed them. And then the nasalized vowels, nasalized lax vowels, started to become less and less distinct with each other because they differ primarily in height distinction, right? I is a higher vowel than E, which is a kind of mid-low vowel. And if you sort of smear the bandwidths of that lowest formant, the first formant, it's hard to figure out exactly where the F1 is located. So maybe Jenkins is just as good a way to say the word or the name as Jenkins. And I think I've told you this story in 341 before, but I used to live in relatively that region of the United States. I went to grad school in Columbus, Ohio, where there were a lot of speakers who did not have that distinction in that context. And I used to listen to a radio station in Columbus, which would have this contest or this promotional game or whatever you want to call it, where they would say a word like in the middle of the day and say, okay, go put this word in our website, and then you'll get rewards for purchasing goods or what have you. So every day, every now and then, like the DJ would come on and say, well, the word now is glass or airplane or something like that. And then one day he came on and said, the word today is spin. And I was like, spin? What the heck is spin? But he was saying spin. I just didn't realize it because instead of his N going to in, it went from in to N. So it doesn't really matter if you're from Columbus or Tennessee or what have you. And we have the acoustics of nasalized vowels to thank for that. Here's another example. This one's kind of fun. It's from this click language. Oh. And you can see the nasalized vowels here really distinctly because all these vowel formants are not as intense as they are in the oral vowel. And they're also kind of broader in terms of their frequency range because we're smoothing out the bandwidth. And I'll just end this by saying that once upon a time I made these part of a production exercise in 341, so I had everybody in the class saying stuff like that, and they all thought it was a funny joke at their expense. So I'll end with that, and I'll never put that in your production exercises again, so at least there's one thing you can be thankful for. Okay, see you next time to talk about laterals and also approximants and stops.